Really glad to be here at NASA. So I was telling earlier that I used to work at Brown University before I moved to Berkeley Lab, and was certainly directly involved in a number of projects associated with Mars and mapping missions and whatnot. So NASA has certainly been, I think, an organization I've always looked up to. So I'm really glad to be here. So I work at the NERSC Supercomputing Center at Berkeley Lab, and at NERSC, I'm responsible for the data strategy, so we think about the software stack to deploy to handle our data users. But today's talk is going to be somewhat specific. We're going to talk about deep learning for problems in climate. So I think given the background of this audience, I thought I'd start slow. So for those of you who may not be totally up to speed on deep learning, we'll just start off with what the industry has done so far, and just maybe clarify a little bit of nomenclature. And then we'll dive into deep learning for climate science. We'll motivate the problem, the specific problem that we're trying to tackle, and a couple of architectures. I'll touch upon scaling. So I'm at a high-performance computing center, so problems that fit on a single GPU are maybe not as interesting to me. I really do need to run on the entire machine. So we'll touch about how you get deep learning scaled to the entire supercomputer. And then I'll sort of step back at that point and talk about other deep learning projects that we've done in science in general, just so you get a flavor for what's possible in science. And then we'll conclude. All right, so let's start with what the industry has been up to. I guess before we get to the industry part, I just want to let you know that deep learning is not new in the sense that it's not the 2010s when deep learning was discovered. Right in the 1960s in MIT, people were fiddling with single layer neural networks. So essentially what you do is you have some input, you apply some weight, some nonlinearity, and you get an output. And people fiddled with that for a while. Unfortunately for this field, very early on it was discovered that such a simple model could not even model something like the exclusive or bit logic problem. And once that was published, essentially this entire field sort of was stuck for 2 decades, which was a real pity. In the mid-1980s, I think people figured out how to get multiple layers to work. So you essentially take some input, you apply a linear weight, you pass it through a nonlinearity, you apply linear weight, pass it through a nonlinearity, and you get the output. And people essentially figured out how to get the multiple layers to work, how to propagate updates through the network. So that was promising. Now, unfortunately, I think again for neural networks, what happened around that time was that random forests and SVMs were the most popular algorithms, and people just ran with it for a while. Till present day, so we are in the third wave of neural networks, and now it's called deep learning. The reason we call it deep learning is because instead of that schematic where I showed you an input and 2 layers in between and 1 output, these networks have many more layers. So this is a contemporary network from an image classification problem. So here's the input, and here's the output, and you can see several dozen layers. So the deep part comes from having many layers. You might ask why now? What is special about this time around for deep learning? So there have been 2 trends, I think, between the mid-1980s and where we are right now. One is big data. I mean, we certainly have access to a lot of data. For deep learning, for the computer vision community, what was critical was that there was a certain data set called the Imagenet data set, which was put together by Fei Li at Stanford, and she essentially put together millions of labeled images. So that was really important for computer vision practitioners. The other, I would say, is big compute. So I'm talking about GTC. The fact is that you can get teraflop class performance on a single node these days. You can just plug in a GPU or a modern CPU and get some really high level of performance. So given those 2 trends, a lot of curated data and a lot of unlabeled data as well, I guess, available, and a lot of compute that's available to you locally, I think it's only now that people realize that if you can make these networks deep, that increases their expressive capability. You have a lot of data to train it on, and by the way, you have compute infrastructure to run it on, that you really understand what the power is of these networks. And I think that's what's really happened here. That the computing has demonstrated the true power, the representative capability of these networks. And that's essentially what we are enjoying in this third wave of deep learning. So just flash through, I think, a few prominent high-profile stories. So certainly, there's been a lot of buzz around the Go system that was developed by DeepMind, which now Google has acquired. And they are using deep learning, a flavor of deep learning called reinforcement learning, to essentially beat the world's leading Go player. Go is supposed to be a game that's exponentially harder than chess, so this is quite an achievement. I think where you are right now, I'm sure you've run into one of these cars, so self-driving cars are no longer science fiction. There are a range of scanners on these cars, so deep learning systems are employed to fuse all of their data and analyze data. But then also the control system, so whether you want to turn to the left or right or hit the accelerator or the brake, that decision is also made by a reinforcement learning system. So that's very much integral to these cars. Speech recognition has been
Advance the slides.
Oh yeah.
Speech recognition has been an open, prominent field, and it's only now that again people from Baidu and Microsoft Research have used deep learning to successfully solve this problem. So these days, if you pick up your iPhone or Android device, chances are really high that you're actually, when you speak to the phone, that there is a deep learning decoder in the backend. And typically there's a deep learning network that's on the phone and also one in the cloud. And the speech signal essentially is decoded by these systems. But really, I think the problem that I think successfully demonstrated that deep learning could work was the Imagenet classification problem in computer vision. So the problem is the following. I'm going to give you a real-world image. So these are just 4 examples. And you, the machine learning or deep learning system, will need to draw me boxes around objects of interest and tell me what's in that box. So for this image, for example, the deep learning system needs to draw a box around the bird and provide it with that label, frog, so on and so forth. So this data set has all the complexities of a natural scene. You have problems of scale, so the bird is much bigger than the frog. You have problems of occlusion, so things occlude each other and they might not be completely visible. You might have problems with illumination, many different kinds of categories. So I would say that I think in the early 2010, 2011 timeframe, a lot of computer vision researchers actually felt that this problem could not be solved in the next decade, that it would take a while before one could solve it. Till deep learning systems kicked in. So around the 2010, 2011 timeframe, what you would see is, each computer vision researcher would try their very best and hand engineer features and tweak them and so on and so forth till they can maybe drop the error rate by 0.25% or 0.5%. And that's generally what the field was doing till about there. Till Jeff Hinton decided to, I guess, call up Jitendra Malik, who's at UC Berkeley, and essentially Jeff Hinton asked him, well, what problem do I need to solve to prove to you that this is working? And Jitendra Malik essentially said, solve Imagenet. So Jeff got together with his Russian grad students and postdocs. Yes.
Yeah, just
Keep it outside. Okay, sure. Sounds good.
I think it's because of your hand. Just if you can not touch the
Yep, that sounds good.
Perfect.
Got it? Okay. So Jeff Hinton took this seriously, and they got convolutional neural networks working at scale. And in that 1 year, they dropped the error rate by about 15% or so. Subsequently, the entire computer vision community has completely switched over to deep learning. That's what they're using. And steadily, over the last few years, they have now dropped the error rates for this Imagenet classification problem to a level that's below what is considered to be human level performance. So for that data set, chances are that the deep learning system will do a better job at object classification than what even humans are capable of. All right, so again, for those of you who may not have seen this stuff before, I just want to walk you through the general nomenclature. We're not going to go into details here. But essentially what you do is to use a convolutional network. You start up with an image, and that image might be, say, 224 by 224 pixels, and it might have 3 channels. And there are going to be many filtering layers. So hopefully you all know about image processing and filtering. So there are going to be some convolution layers where you just take a filter and you slide it across the image, and then you apply that linear weight essentially. And then there are these things called pooling layers, which is this non-linearity. So given a bunch of 3 by 3 pixels, say we just choose the one max value out of that area. And you do this successively. So you apply convolution and pooling, so on and so forth. There are some fully connected layers right at the end. And then out at the end of the network is supposed to say how confident I am about, these 100 categories. So the way these networks works is the following. The very first step is that you need to identify some training data. And typically training data consists of, say, images and labels that you know for a fact are in that data set. Somehow you will need to decide on what the architecture of this network needs to be. So how many convolution layers, how many pooling layers, the number of filters that you have. Once you've decided on that architecture, you randomly initialize weights. You provide input data, so let's say you just provide one image. You pass it through the network, and then you get a certain output. Now, because you know what the ground truth is, you know the label for that image, you can see whether you've done the right job. Did you get the correct answer? If you made an error, then essentially what you can do is you can take the derivative of that error with respect to all of these parameters and pass or backpropagate that error through the network and tweak it so that it does a better job in the future. And you do this millions of times. So you're going to pass more images through the network, compute the error, backpropagate the error, and update the weights. And hopefully you'll get a network that does the right thing. Now, I think the reason I believe why a lot of people got excited about this field was that when you do that process, when you backpropagate the network, backpropagate the errors through the network, you actually get weights that look really interesting. And visually, from a neuroscience perspective, there are interesting things that the network is doing. So, for example, if you look at the convolutional network right next to the image input, the weights that we learn essentially correspond to Gabor functions. So these are scaled versions of edges that the network has essentially learned. And it is known that in the human visual system, that's what our neurons are doing. That's what the V1 neurons do. If you go to the next convolution layer, essentially what you see are simple texture patterns, so combinations of edges that form simple textures. Go to the next convolution layer, you essentially see texture patterns being combined to form parts of objects. So, this might be a texture pattern that maybe corresponds to a clock. This might correspond to a wheel, and so on. And then finally, right at the end, you essentially get patterns that correspond to objects themselves. So this was really interesting because the network was never told to learn this hierarchy per se, or the fact that objects are composed of parts which are composed of texture patterns which are composed of edges. This is what the networks learn organically. So that got, I think, a lot of people in neuroscience excited, and certainly a lot of computer vision people excited, because so far what the computer vision folks were doing for the last 30 years is that they were just hand coding features for objects. They would say, oh, I know how to design the world's best pedestrian detector, and I know how to find gaps in images and so on and so forth. But in this case, we've just left it to the network to figure out what sort of filter weights make the most sense for the problem. All right, so hopefully I think that gives you a sense for industrial applications and at a very high level how these networks work. So I'm going to move into how we can apply deep learning for climate science. Since a bunch of you are earth scientists, I guess I'd say that the science problem of interest for us is how extreme weather is going to change in the future. Clearly, discussions around the average sea level rise or the mean global temperature are of interest, but you wash out a lot of detail when taking a large data set and just compressing it down to a single number. So in this case, what we want to ask is, if we want to look at high resolution, spatially resolved extremes, do we expect extremes to become more frequent in the future or less frequent? Are they going to become more intense or less intense? So that's the question we want to address. So again, you all know this, but just to give you some visual examples, so this is Hurricane Sandy. So a storm system that had a very large spatial footprint. And the kind of question that one might want to ask is, these storm systems, so a tropical cyclone or an ex-tropical cyclone, do we expect such storms to start making landfall more often? And once they make landfall, are they going to be, say, a Cat 4? What is the intensity going to be like when they make landfall? We all know about Hurricane Katrina and the associated surge and the amount of damage that it did. So again, these events are devastating, I would say, to economies. And the question for a city like New Orleans, it's almost taking them a decade probably to recover from the storm. So this question of are we going to start experiencing the storms more often or less often is really important, I think. Closer to home for us, I guess in California, where fortunately we don't see a lot of storms, but we definitely see atmospheric rivers. So atmospheric rivers are systems that advect moisture from the tropics, and over the course of 4 to 5 days, they just drop it all in place. So a lot of rain, I think 50% of precipitation for California occurs through these events. And you would like to know whether, for example, these events are going to move northwards and just skip, for example, the Bay Area, or if there is no change in the dynamics of these storms, when they do carry water vapor and drop it, are we going to experience more precipitation because of cluster clapeyron and the fact that there is more water vapor in the atmosphere? So in all cases, essentially we will look at simulation data, and then we will automatically extract such patterns from the simulation data. And once we've been able to extract it in an unbiased quantitative manner, then you can start asking questions about whether there is change. So I can run the tool for a baseline climatology, and I can run the same tool for a climate change simulation where you've maybe added more CO2 into the atmosphere. So the tool, the data is always going to be a simulation for us, and I just want to give you a visual sense for what the data is like. So this is a CAM5 quarter degree model that we routinely run in production on our supercomputers. And at that resolution, at 25 kilometers, you can see these extremes. You can see tropical cyclones forming. You can see ex-tropical cyclones. You can also see atmospheric rivers. So we do believe that these models have enough fidelity spatially, temporally, and also in the physics that it does make sense to do this sort of analysis. Now the challenge, of course, is once you run this model out, so if you're talking about 25 kilometers, if you run this out for say a decade or maybe a century, you are talking about tens of terabytes of data. That does need to be analyzed. All right. So one challenge, I guess, compared to say Imagenet is that our images are not RGB anymore. So again, if you take a consumer camera and just click images, you're going to have 8-bit RGB data at each pixel. We will have, say, 1,000 by 1,000 pixels, so that's about 1,000,000 pixels. But then at each location, of course, we have many different fields. Right? So we have water vapor and wind and pressure and temperature and so on and so forth. So typically we'll have a few dozen channels at each location. And we want to provide all of that data to the machine learning system, and the machine learning system should figure out what channel is informative and what is not. So the task will be that I'm going to give machine learning system all of that data. So 1,000,000 pixels, say 16 channels per pixel, and its task is going to be similar to the Imagenet task: draw me bounding boxes around the extreme weather events of interest. So here there are some yellow boxes around tropical cyclones, and a red box around atmospheric rivers, and a green box around ex-tropical cyclones. So that's going to be the task that we'll ask the machine learning system to solve. Does this make sense? Any questions so far? Okay. All right. So if at this point, I think if I had to just draw a high-level analogy between what we want to do here for climate science and what's being done for Imagenet, and clearly there is an analogy in terms of the task that we want to solve. So we essentially have a pattern classification task, and implicitly I want the machine learning system to figure out what features make sense. So the feature learning problem is going to be solved by the machine learning system. I'm not going to be in this business of hand coding features that by hand to get it to work for tropical cyclones or atmospheric rivers or whatever. But there are some differences, as I mentioned. So this is multi-channel data. It's certainly higher precision. We don't have 8-bit values that we're operating on. But And of course our patterns are spatio-temporal, so different patterns have different spatial extents and different patterns last for different periods of time. But there is an important thing to realize, which is maybe a little subtle, which is that the underlying statistics of these events are likely different from what you might encounter in Imagenet. So specifically, if I take a camera and I just shoot images of the world, so again, you might have 1,000 by 1,000 pixels, so essentially one image is a point in a million-dimensional space. So I go around taking images of the world, and I'm slowly populating this million-dimensional space. And in the Imagenet problem, essentially what it boils down to is, can I learn a classifier in this high-dimensional space that can separate cats from dogs? That's essentially the problem we're going to solve. Now, for climate, you have a fluid flow simulation. You're not collecting, images of the world. It's a million-dimensional, maybe 16 million-dimensional if you want to consider all the channels. There is really no reason to believe that the statistics of clusters of, say, atmospheric rivers or tropical cyclones or ex-tropical cyclones are going to be similar to what you encounter in the natural scene. So the question really is, in this high-dimensional space, for climate data, are you going to be able to find classifiers that can separate out these patterns? So I guess is deep learning powerful enough to be able to do that classification problem in a high-dimensional space? So that's the problem, essentially. All right, so now, I guess now that you hopefully understand the setup of the problem, we're going to apply two techniques. So we'll apply the supervised convolution architecture, which is quite similar to the Imagenet problem. And then we'll apply a more advanced version called the semi-supervised formulation. We'll get to that in a second. So let's start with the supervised architecture. So I guess for this project, so we've been working on this for about 3 years now. And essentially, I guess I needed to convince myself that deep learning could work for scientific data. And again, as I mentioned, the statistics are different compared to natural images, so I think we just have to prove to ourselves that this works. So for supervised learning, we started simple, and what we did was for training essentially, we would crop out nicely centered patches of this simulation data set where we knew that there was a tropical cyclone. And let's just stick to maybe just a tropical cyclone, just for illustration purposes. So, how do you pull that out? If you're lucky and, the climate science community has a ground truth on hand, a catalog on hand, then that's something, of course, that you can use. And that's something that we actually use for atmospheric rivers. For tropical cyclones, as discussing earlier, that there are some heuristics in the community that people seem to be comfortable with. So we just implemented those heuristics, and we're going to say that that is ground truth. I mean, that's what the climate science community seems to agree on. So somehow, I guess, either through ground truth catalogs or through whatever the most widely accepted heuristic is, we're going to get a handle on what we consider to be patches that contain tropical cyclones for sure. And then we'll just randomly choose other patches that will not contain tropical cyclones. And that's going to be our positive and negative labels for our machine learning system. Now, given that data, so raw data and labels, I'm going to ask the network to just solve a very simple binary classification problem. I'll ask the network to predict whether a new patch that it's never seen before, whether that contains a tropical cyclone or not, yes or no. So that's the entire task of the classifier. All right, so just some specifics on, say, for the tropical cyclone problem, we are working on centered, cropped 32 by 32 image patches, a bunch of fields that we are using, and then about 10,000 positive and 10,000 negative examples. Now, this is really important because I think empirically what's been found in the deep learning community is that to get these networks to work for tens of thousands of classes, you need 100,000 examples, preferably 1 million examples. In this case, our problem is not as hard, but I think empirically, again, I think what we find is that we need thousands of examples and preferably tens of thousands of examples. Now, this also, of course, restricts the depth of the architecture that we can train. If you have a very, very deep architecture, it's not going to be sufficient to use a few thousand examples. So anyway, so given I guess this amount of data, this is the architecture that we ended up with. So we have, again, input images. We have a cascade of convolution pooling layers, and then we have a fully connected layer. And then in the end, it's a binary classification task. That's all you need to do. So we trained separate networks for tropical cyclones, separate network for atmospheric rivers, a separate network for weather fronts, and those are the specifics on the architecture. But generally, it all looks like that. So the architecture is relatively shallow. That's important to understand.
I have a question.
Yes.
So in the previous slide,
Yes.
you said you need thousands of examples.
Yep.
So I'm not really sure about that, what you mean by thousands of examples. They all have to be different from each other, so that you're capturing the entire range, or, what do you mean by that, Because let's say a tropical cyclone, if you look at the entire record, you may have only a few thousand.
Yeah, so in this case, so first of all, the more diverse your population set can be, the machine learning system has a better chance of capturing that variability. So clearly, you should make it fair in that if you're only going to be presenting tropical depressions to the machine learning system and no Cat 5 storms, then the machine learning system is going to have a hard job in picking out Cat 5 storms. So let's assume that you've done a fair job of capturing the variability in the so-called appearance of the storm system. So let's assume that that's the case, which in our case, we made sure that was the case. For atmospheric rivers, our domain scientists had by hand picked out patterns that had made landfall on the west coast. So all of the variability in atmospheric rivers was in some sense captured. Now we are actually, I'll get to it later on, but we are not. We are treating this as an instantaneous image classification problem, and we are ignoring the temporal extent. So while you might have only a few, about 70 to 80 tropical cyclones in a year, and say if a tropical cyclone lasts for 10 days or 5 days, we will actually consider every single day as a labeled example. So it's not 70 to 80 storms a year, but 350 to 400 or more. If you consider the temporal evolution of the system, if you took that into account and reduced that as one example, that would certainly cause problems in the amount of instances of the event.
Okay, so if you're taking temporal sequence,
Yes.
But what is it that you're getting, by including more and more? Because it's the same feature, really, just moving a little bit, isn't it?
Well, not quite. I mean, if you track the evolution, from cyclogenesis to storm intensification to dissipation once things make landfall, certainly a lot of things are changing. So I think if you look at that spatio-temporal volume, then you will see variation there.
So you're looking at a lot of other variables, probably, not just the visual appearance. But
Correct. So all of these variables are being tracked. Yeah.
Thank you.
Sure. All right. So to recap, we have an architecture, we train it, and now the question is, well, how well does it do? So here are some numbers. So let's just focus on tropical cyclones for the time being. The numbers being plotted are accuracy numbers, so for a held out test data set that the machine learning system has never seen before, where we know what the ground truth is. How well does it do in this binary classification task? So the very last column is on the convolutional network that I showed you in the last slide. And I guess the test numbers are the one that maybe you should be focusing on. Now for comparison, we put in other baseline machine learning methods, so logistic regression and k-nearest neighbors and SVMs and random forests. So I guess one, I think high-level observation is that in general the numbers look good. I mean, it's all 75%, 80% plus. So for me, I think what that tells me is that the climate science community in general has really not taken machine learning seriously. Machine learning methods are really not very commonly found in the climate science community. So anyways, I guess that's one high-level observation. Now, if I were to compare the performance of deep learning systems to other methods, generally I would say that across the board we are getting state-of-the-art performance with deep learning systems. I mean, once in a while you'd see some other method doing maybe equally as well. But across the board, I would say that they're doing fairly well. So really, I think the message there is, before you apply deep learning, which by now, hopefully, I guess you appreciate is the most powerful machine learning method there is, maybe you should start slow. So start with the easier methods like logistic regression or KNNs, and get a better sense for how hard the problem really is. I mean, if you're getting 99% accuracy with KNNs or logistic regression, then maybe you don't care about getting to 99.1% with deep learning. So anyway, so I think it is important, I think, to have these baseline comparisons to better appreciate how easy or hard the problem is. I'll also note that tuning the network is hard. Sometimes you have these other methods also have a parameter associated with them. So for k-nearest neighbors, you have to come up with the choice of k. For support vector machines, you have to come up with the choice of basis function and so on. So you do need some automated way for you to explore that space. Yes, the question is?
Question on these statistics. The weather fronts in the last example, the test is actually better than the train, and I'm wondering if that's because there are actually bounds on those numbers, and that's just kind of an accident, a happy accident.
Yeah, I guess in an ideal sense, if your test set is, so it's probably a convenient accident, I guess, in this case. Ideally, the statistics of your test set would match the statistics of your training set. In this case, it may very well be that what's happened is that we got some easy models to classify the test set.
Thanks.
Sure. I guess the one thing you don't want to happen is to have a very high train number and then that number drops for tests. That means that you've overfitted the model. All right, so I guess the purpose of this exercise was really to, I think, convince myself that convolutional architectures would do a good job, and it does seem to be doing a good job. So now we're going to step up our game. So we'll have a harder version of this problem. So something called the semi-supervised learning problem. Yes.
One question.
Yes.
So we have one question from the audience, Michael Segal, and he has a technical question. Just starting to use CNN, previously used NLP, neural nets. The inputs are, for example, 32 by 32 with 8 variables for the DC. So how does the input is defined into the network? Since the inputs to CNN usually expects an image, grayscale or RGB, which is 32 by 32 times 3. So basically he's trying to talk about the bands. How are you actually feeding in all the bands? So
yeah, so we're not quantizing or compressing the information, and we are feeding in the raw single precision numbers to the deep net. And fundamentally, there's nothing that constrains us from doing so.
But so the question is, in the input nodes, are you actually feeding in multiple bands or
Yes.
just? Okay.
So we are feeding in all 8 channels. We are not converting into a visual image that's just 3 channels.
Okay.
So we are feeding it single precision data that
8 channels.
8 channels. Yep. All right. So so back to this formulation. What we want to do now is, so we trained 3 separate networks that were individually doing a really good job. But what I really want to do is to have one single unified architecture that can pick out all patterns. I don't want to have 10 different architectures doing 10 different things. Now, recall that I nicely cropped and centered my training data. That's not going to be the case always. So I would like that network to predict bounding boxes for where these events are. And then this last point, I mean, this is sort of a holy grail problem. But we know that events like tropical cyclones, extropical cyclones, atmospheric rivers are well studied. But there might be some patterns for which we don't have a lot of label data. And in some cases, we might have no labels at all. So ideally, I guess you want an architecture that can pick out these patterns as well. All right, so that's going to be the goal for the semi-supervised learning problem. All right, so this is the architecture that we came up with. There are 3 pieces here. So there is the encoder piece, the decoder piece, and then the piece that predicts bounding boxes and class probabilities. So for the time being, we're going to ignore the decoder piece. So we start with the encoders. You take the raw data, so 32 by 32 by 8 or more. You apply these convolution pooling layers. You get it to this representation, and then from this representation, you essentially ask the network to predict bounding boxes and class probabilities. So far, that's your conventional convolutional network. Nothing's really changed. But of course, this architecture has a twist, and the twist is the decoder piece. So essentially what the decoder does is to operate on the same compact representation, and then progressively deconvolve, or in some sense upsample the data set, till you get an output that matches the dimensionality of your input. So during training, essentially what this network will do is to solve two objectives simultaneously. One, it will try to match it'll try to make sure that the output matches the input. So there is a reconstruction quality associated with this network. And two, it's going to try to predict objects and the bounding box locations. So for objects and bounding box locations, similar to the convolutional supervised problem, we have ground truth data for tropical cyclones and ex-tropical cyclones and atmospheric rivers. So the network is able to take that into account. For the decoder piece, really, it doesn't. I mean, naively, you can think that maybe all the decoder could have done is just copy every single input pixel to the output pixel, and it's done, perfect reconstruction. But we are forcing it to go through this bottleneck layer, and because the network is trying to make predictions for object types and bounding boxes of this bottleneck layer, if this network succeeds, then I guess all of the interesting dynamics has been captured in this bottleneck layer. So that's what the semi-supervised formulation is, the architecture that we ended up using. And I guess I can show you some results. So first, the reconstruction results. Again, recall that we have some input data coming in, it gets filtered, passed through the bottleneck layer, and then there is a decoded version. So these 4 images here are, again, raw CAM5 fields. And then the reconstructed version at the end of the decoder layer is out on the right side. So in general, I think the spatial variability seems to be getting captured fairly well. I think the results look reasonable. Now these are the classification and regression results. So again, recall that the job of the network is to move a box to where it thinks the pattern is, and then associate a label to it. So ground truth in this case is in green, and then the network prediction is in red. So I guess one good news is that a single network is able to move boxes around for ex-tropical cyclones and atmospheric rivers and tropical cyclones. So that's good. So I think the goal of working towards a unified architecture in some sense is on its way. The sizes of the bounding boxes aren't quite right. So we know that there are some deficiencies in our implementation. And we are missing a few events as well. So there's work to do here, but I think there is promise in solving this localization problem. Now the third criteria, I think that's the hardest one, and of course we're not going to solve it all in one shot. So the third criteria was on discovering new patterns. So again, recall that the bottleneck layer seems to be doing a good job at predicting, the localization task, and also reconstruction. So what one can do is to look at a clustering of the weights that have been learned in the bottleneck layer, and see if you're maybe able to separate the tropical cyclones from the ex-tropical cyclones from the atmospheric rivers in this phase. So all the gray dots here on this display essentially corresponds to the weights that have been learned. And then the 3 colors, the blue, red, and green, correspond to the 3 known event types. So right now, ideally, I guess what I would have liked to see is maybe 5 to 10 clusters where the blues were separate from the greens, were separate from the reds, but that's not the case right now. So clearly, there's more work to do. But assuming that one day we're gonna get there, I think the question that one will ask is the following. So let's say that the blue clusters are all here and they all correspond to say ex-tropical cyclones. If there is a cluster that's gray and that's not yet labeled, I think the question then one can ask is what is up with that cluster, right? Is there a semantic label that we can associate to that cluster? So that is, I think, where the discovery part comes in, and we're not there yet, but I think it's headed in the right direction, I believe. All right, so